Hi, my name is Matt Powers, and today I'd like to talk about NMR, or nuclear magnetic resonance. Basically, nuclear magnetic resonance is a physical phenomenon that we can observe in the real world, not just in the lab setting, in which nuclei that have certain magnetic properties absorb and re-emit electromagnetic waves when you subject those nuclei to a magnetic field of varying strengths. Basically, the radiant energy that is emitted by these nuclei is interpreted in a lab setting as a specific resonance frequency. That resonance frequency, it depends on the strength of the magnetic field surrounding the nuclei and the properties of the isotopes of that nuclei. Usually the resonance frequency is directly proportional to the strength of the magnetic field that you're applying to that nuclei. So knowing this, organic chemists, they like to, or they find it easy to test this in a lab setting using spectroscopy. The formal definition of NMR spectroscopy is the exploitation of the magnetic properties of atomic nuclei in order to determine certain physical and chemical properties of certain atoms in larger molecules. Those certain physical and chemical properties can include the size of the nuclei, the dynamics of the molecule that we're looking at, the reaction state of the nuclei that we're observing, and the environment of the specific types of nuclei that we're looking at. By environment, I just mean what other atoms are surrounding that specific element that we're looking at. Usually, spectroscopy is divided into two main types. You have, let me erase this real quick. You have Proton NMR, and you have carbon-13 NMR. And Proton NMR looks at very small nuclei, usually belonging to hydrogens. And that's usually a one-dimensional analysis of whatever certain nuclei we're looking at. Carbon-13 involves bigger molecules. It can go all the way up to, you could be looking at phosphorus, which has an atomic number of 31. So larger molecules, we're looking at 3D and 4D shapes. But today I'm going to focus on proton NMR since it's a little bit simpler than looking at the larger molecules, a little bit easier to explain. So we're going to focus on proton NMR. Now, generally in experimenting, you start with the specific molecule you're looking at. So if you're looking at proton NMR, it's going to contain hydrogens. You keep a fixed radio frequency applied to that molecule, and then you submit that molecule to varying magnetic fields, or a varying strength. And usually, it's hooked up to your apparatus. You'll have computer software set up that help you analyze the magnetic frequency that you're applying, or the magnetic field that you're applying to your molecules, and a graph will be spit out to you afterward that looks something like this. It's going to have your y-axis going to be the frequency of the resonance emitted from each nuclei, and your x-axis is going to be the delta values ranging from 12 to 0. It's read from right to left. This side of the graph is called the upfield part of the graph, and this side is the downfield part of the graph. 0 over here is a high magnetic field, and 12 is a low magnetic field. Each peak represents a certain area of absorption, or where the nuclei absorbed the magnetic field and emitted the radiant energy. So depending on the areas of absorption, or depending on the height, the size, on where the peak is located, we can determine the number of protons in the molecule. We can determine the different kinds of protons, and by that I mean where the protons are located, or what molecules are surrounding them. That also has to do with the environment that I mentioned earlier. And the number of protons of the certain types. So in analyzing the graph, we look at it and we see the number of signals emitted. And by signals, I mean the number of peaks. The number of peaks tell us how many different kinds of protons. So this peak of this height signifies a certain type of proton molecule. So maybe if we were to make up a molecule right now, let's just do a sawhorse structure with hydrogens coming off. Maybe this type of hydrogen would show up as this kind of peak. And this hydrogen in the middle coming off this is a CH2 carbon, would show up as this kind of peak. So that's what the number of signals tells us. It tells us how many different kinds of protons we have in our molecule. In this case, the sample molecule, there's just two types. We have the protons on the CH3, the methyl groups over here, and then the protons on the CH2. And the location of the peak on the graph tells us how shielded or unshielded the proton is. And by shielded, I mean how many electrons are surrounding it and protecting it from that magnetic field, deflecting it, not more so than protecting it. The intensity of the signal, or the height, or maybe not the height, the integration, the area under the peak, tells us the number of protons of that type. So a peak with a larger area would tell us that there's more of that type of proton. So again, if we're assuming that this peak is representing the protons on the methyls, we would see that there are 6 hydrogens off the methyls, so it's going to have a larger area than the protons coming off the CH2. So there's a smaller area under this peak. There's also signal splitting, which the peaks can be split into singlets like these, or doublets or triplets, in which you have multiples of one peak. And those tell you the number of protons on the adjacent atoms of the proton that you're looking at. So that kind of gives you clues to the environment of the proton that you're looking at. The location of each peak corresponds with a certain number on your graph. So down here, this peak shows that a certain nuclei responded to a low magnetic field. And the number 10, marking where the peak is, shows that there was a chemical shift on that nuclei in parts per million. And that's pretty much just the general analysis of how you would interpret the graphs. Again, this just as an overview, from this you would learn the size, the environment, the number of protons, and the types of protons.